In this video, I'm going to illustrate how to run a multiple regression analysis using the statistical package STATA version 14, and I'm going to focus mainly on the demonstration of various drop-down menu options. So basically, multiple regression is utilized when you have a set of predictor variables and you are trying to account for variation in a criterion variable. Predictor variables are also referred to as independent variables, and the criterion variable is often referred to as the dependent variable. So basically, the dependent variable in multiple regression is assumed to be continuous. The predictors generally are treated as continuous, but multiple regression will support the use of a dichotomous predictor or independent variable in the model. So you can incorporate dichotomous predictors in the statistical model. So to illustrate this, we actually have to get some data and pull it into STATA. So just kind of note, if I wanted to actually create a data set, I can just go to Data Editor, and edit, and I can actually, using various commands here, I can actually create variables and incorporate their values on those variables, and that would work. But actually, for the purposes of this demonstration, I'm just going to import some data from Excel or an Excel file. So I'll click on File and go to Import and Excel Spreadsheet. And if I click on Browse, then I've actually set it up to where it goes to the right drive and appropriate folder. So I'm going to click on this file right here that contains my example data. So I click on Open, and you can see that I've got my variable names and then the data that follows. Actually, I want to import with the first row being the variable name, so I'm going to click on that, and you can see what happens in terms of with the import wizard. So the variable names now appear in this row. So I'm going to click on OK, and now the data has actually been imported into the program's memory. And so when I look at, go to Data Editor, and I'll go to Browse, because I don't want to really change anything with the data. You can see I have my variables gender, subject matter interest, mastery goals, anxiety, and achievement. So these are my variables in the data set. Each row represents a different case, so it could be a person's responses to each of these variables in terms of gender and subject matter interest and so forth. So I've got it set up to where gender is coded 0 for male and 1 for female, and then these are scores on the other measures. So for the current examples, gender is obviously a categorical variable that's dichotomous, so it can actually be incorporated as a predictor in a regression model, and then these variables are all being treated as continuous. So like I said, the data has already been imported into memory, and so we can run our analysis. So I'm going to click on Statistics, Linear Models and Related, and click on Linear Regression. And here I will type in, or actually there's a little drop down to identify the dependent variable. I'm going to use achievement, and I'm going to actually use these other variables as predictors of achievement. So I'm going to use achievement as my dependent variable, and then to get my independent variables and also note their measurement properties, I'm going to click on this little box right here. And so where it says, add factor variable, basically what we're going to do is there's a little drop down here, and essentially what I'll do is I'll be adding in my predictors in the model. So we'll start with subject matter interest, which I'm treating as a continuous predictor. So I'll click on that, and then click on C because it says check to treat variable as continuous. So I want to treat that as a continuous variable, and I'll click on Add to Variable List. Then I'll do the same for mastery goals, click, and then I'll do the same for anxiety as well, and I'll click on that. If I want to add gender and I want to treat that as a categorical variable, then I would unclick this and then click on Add to Variable List. And you'll notice that it has a little I.gender right here, and that's denoting the fact that it is being treated as a categorical variable. So at any rate, I'll click on OK, and now you can see we have our predictors listed in the independent variables box. If you look under standard errors, robust, you actually have a number of different options in terms of your how you want to compute the standard errors for your tests of the regression coefficients. You actually have least squares, which is what we're going to be using, bootstrap, jackknife, and so forth. So we're going to stick with least squares right now, and that's actually the default. So, but we'll click on that. Under reporting, you can ask for standardized beta coefficients, or basically it's the regression coefficient for z-scored variables. So we'll click on that. So this is just basically your beta coefficient that's going to now appear in your output. So now we'll click on submit, and we get our regression results. So you'll notice that first of all, you have your r-squared value, or r-squared value, and think about it as the proportion of variation in your criterion variable or your dependent variable that is explained by the set of predictors. And when I use the term explained, I'm not necessarily meaning this in a causal sense, just in terms of the variance that's accounted for. So at any rate, in our model, our basic model, we had mastery goals, anxiety, gender, and subject matter interest as predictors. So we had, basically subject matter interest as a predictor. We had anxiety as a predictor. We had mastery goals as a predictor. And we had gender as a predictor in the model. Okay, so these variables were being used to predict achievement. Okay, so the test of the r-square value that you see reported is really addressing the question of, how much variation does the set of predictor variables account for in the criterion variable, which is achievement. So you can see that as a set, or as a unit, these predictor variables accounted for about 36.27% of the variation. So if you just multiply the r-squared value by 100%, then you can represent this in terms of a percentage. So the F test that you have right here, this is the observed F value that's based on the data, and then you have a significance level. That's the probability value, or the p-value. The p-value for our analysis is 0.0004. So basically what this is all about is that you're testing whether we can infer within the population that the r-squared value is greater than 0. So in other words, it addresses the question: can we infer that that within the population the predictors account for greater than 0% of the variation in the criterion variable, which was achievement. So at any rate, just kind of the test basically involves using the p-value that's printed out here. So this is p is equal to 0.0004, and essentially the p-value is compared against an alpha level that you set prior to actually running the analysis. So the alpha level is essentially your tolerance for committing a type 1 error, which is to say that it's your tolerance for effectively stating that for this particular test, stating that that within the population the correlation is greater than 0. The r-squared value is greater than 0, when in fact the population r-squared value is actually 0. So we set an alpha level, and that alpha level is compared against the p-value. And the conventional alpha level that most people utilize, and and you see generally in the research literature is an alpha threshold or level at 0.05. So the general rule of thumb is that if the p-value that's printed out is less than or equal to the alpha level at 0.05, then you essentially reject the null, and from that you would infer that that within the population population R-square is greater than 0. So in this particular case, that's what we would infer based on this data. There's our p-value, there's our alpha level, and that would be our inference. Note too that you also get an adjusted R-square value, and essentially this is a descriptive index which provides obviously an adjustment to the R-square value that's presented right here, and it's adjusted downward based on the number of predictors and the sample size. What happens is that as if you have smaller sample sizes with larger numbers of predictors, then the model oftentimes is overfit to the data, which means that the R-square value actually is systematically overestimates the true population R-square value. So the adjusted R-square is just sort of a more calibrated R-square value, which tries to remove some of the bias that we see with the R-squared value. Nevertheless, the significance test is a test of the R-squared value as opposed to the adjusted R-squared value. So at this point, what we're saying is that when it comes to the R-square value, that this value is statistically significant. So I'm just going to put a little asterisk right here. After that, then we want to look at the individual predictor variables to see which ones are significantly related to the criterion variable. So each of these regression coefficients that you see printed out right here have a test associated with them. But nevertheless, the regression coefficient, which is denoted as B, these are actually called unstandardized partial regression coefficients. And the way that you would interpret them is to say, like for the first one, subject matter interest, we would say for every one raw score unit increase on subject matter interest, there's a predicted 0.588 raw score unit increase on achievement, which is our dependent or our criterion variable. So we would say for mastery goals, we would say for every one raw score unit increase on mastery goals, there's a predicted increase of 0.47 raw score units on achievement. For anxiety, we would interpret this to mean that for every one raw score unit increase on anxiety, there's a predicted decrease, since the coefficient is negative, of 0.137 raw score units on achievement. And then when it comes to the gender variable right here, basically, you have just two groups. You have a group coded 0, which in our case was male, and a group coded 1, which was female. So if you have a positive relationship right here, that would mean that essentially the group that is coded 1, as in our data, has the higher mean on the achievement variable than the group that is coded 0, which is, for our case, it was the males. If the coefficient was negative, that would mean that the group that scored higher on the dependent variable was the group coded 0 as compared to the group coded 1. So in this particular case right here, just looking at the general regression coefficients, again, it looks like we have a positive predictive relationship between subject matter interest and achievement, a positive predictive relationship between mastery goals and achievement, a negative predictive relationship between anxiety and achievement, and gender has a positive predictive relationship where essentially females, which were coded 1, were scoring higher on achievement than males. These are all partial regression coefficients, and what that means is that when we look at the relationship between each individual predictor and the criterion variable, we are controlling for or partialing out the relationships they share with the other predictor variables. So that's sort of descriptively what these coefficients are kind of capturing. These coefficients are being used as estimators of the population unstandardized regression coefficients. And one of the things that we want to do is to test whether the population regression coefficients are significantly different from 0. So with any of these statistical tests, you're essentially comparing a null hypothesis, which is essentially a hypothesis of no effect, against an alternative or a research hypothesis of some type of effect. So, for each of these regression coefficients that we see right here, the null hypothesis is that beta is equal to 0. In other words, the population unstandardized regression coefficient for each of those predictors is 0, meaning that there's no predictive relationship between the predictor variable and the criterion variable. On the other hand, you have several different possible alternative hypotheses. There's the hypothesis as an alternative hypothesis that beta is not equal to 0. And in this case right here, this is referred to as a non-directional hypothesis, or excuse me, yeah, a non-directional hypothesis. And what that basically means from a significance testing standpoint is that, essentially we're utilizing the sampling distribution of t in order to test out our hypothesis. So a non-directional hypothesis means that essentially when we're testing our null hypothesis, which is actually located in the center of the sampling distribution, so this is our null, which is that beta is equal to 0, we actually we sort of set up our sampling distribution where we have regions where we say, okay, if our data takes us out into this tail right here or this tail up here, then we end up rejecting the null, and we would conclude that our regression coefficient is significantly different from 0 in the population. That would be our inference. So the area in this tail and this tail, this is referred to as the region of rejection, and this is where you would reject your null hypothesis. The area in the center of the distribution is where we do not reject the null hypothesis. So if our regression coefficient based on our data lands us in this area of the sampling distribution of for the unstandardized regression coefficient, then we would maintain the null and we would not adopt the alternative hypothesis. So if our hypothesis is this, essentially a non-directional hypothesis, then that implies what is called a two-tailed t-test, and that's what we are testing out right here. So if our sample result lands us here or in here within the upper or lower tail of the sampling distribution, we reject the null hypothesis. So let's say, for instance, that that subject matter interest, I had hypothesized that it would just simply be related to achievement. In that case, then I would be laying out a non-directional hypothesis, and then I would be testing that out. So you'll notice that in essence, that these p-values right here are basically probability values for two-tailed tests. So these are basically p-values, which I was describing up here for the f-test. So at any rate, the way that you would interpret these is the same way that you would interpret the p-value up here for this particular test, which is that if the p-value is less than some pre-specified alpha level, which again conventionally is 0.05, then you would reject the null. So for subject matter interest, the p-value was less than 0.05. We'll just use that as our criterion. So we would reject the null hypothesis and conclude in favor of the alternative. Given that the value is positive, the null value, by the way, is, again, that beta is equal to 0. And we observed a regression coefficient, which, again, beta is being estimated by our sample regression coefficient. So it's being estimated by that. So here we had a sample coefficient of 0.588. So that that 0.588 is basically landing us in the upper tail of the sampling distribution because it's a positive value. If the value had been negative, then it would have landed down here. So it's taking us in this region right here. and given that our p-value is less than 0.05, we would reject the null and conclude that yes, that within the population, or we would infer that within the population, subject matter interest is a significant predictor of achievement. So the next thing to note is, kind of looking at mastery goals, and you can see that again we have a positive predictive relationship. Is it statistically significant? If we were adopting carrying out a two-tailed test, obviously it would not be, because our p-value would be less than the 0.05 threshold. There is another type of alternative hypothesis, and that's called a directional hypothesis, and within that there are two subtypes of directional hypotheses. So one of the alternative hypotheses is that beta is greater than 0. And so if we were drawing out our sampling distribution of t, what that would basically mean, if we put our null hypothesis in the center of this distribution, so this is the null hypothesis, and in this case right here, the directional hypothesis would imply a one-tailed t-test. So we would essentially put our region of rejection of the null in the upper tail of that sampling distribution. So so for us to conclude that in favor of the null, in favor of the research hypothesis, what we would have to do is to look at a couple of things. First of all, is our predictor variable, is our regression coefficient consistent in terms of the direction of the relationship with what we had hypothesized? Ordinarily, you would suspect or hypothesize that mastery goals would be a positive predictor of achievement. And so we see that we have a positive predictive relationship right here, so we would be putting our region of rejection in the lower tail. And so what we see, though, is that our p-value is actually equal to 0.192. So if we compared this to our alpha threshold, then obviously we would not reject the null. But there's one little pivot point that I want to mention, and that is that the p-values that are printed out are for two-tailed tests. And all things being equal, the two-tailed test, which is testing a non-directional hypothesis, is less powerful than a one-tailed test. So technically speaking, the true p-value is actually half of this. So if we want the actual p-value for a one-tailed test, we would say, we would use the following. We would say p divided by 2 is really the p-value that we should be using to compare against the alpha level. So in this particular case right here, if we divide 0.192 in half, essentially it would be 0.096, so 0.096. So if we compare that against our alpha level, we still are unable to reject the null. But you can see that it's, obviously it's looking closer to 0.05 than what we had previously using a two-tailed criteria. So the thing about it is then that our regression coefficient, it's still landing us in this little region right here of our sampling distribution, because it is a positive value. It's just that it's not taking us far enough out into the tail in order to be able to reject the null. So in this case, we would fail to reject the null hypothesis, and so we would essentially be saying that mastery goals is not a significant predictor of achievement. By the same token, too, if let's say mastery goals had been a negative value for some crazy reason in our data, then it would have landed us out in this region, and we still would not have been able to reject the null. So this is our region of rejection. This is all the region of non-rejection. So let's look at anxiety. And ordinarily, I would hypothesize if there was a relationship, it would be that anxiety would be negatively related or negatively predictive of achievement. And that would reflect a second type of directional hypothesis, where it is essentially that beta is less than 0. So in this particular case, if I'm testing this out using our sampling distribution of t, which which is essentially just a conversion of the sampling distribution of the regression coefficients. Then in that particular case, I would be placing my region of rejection in the lower tail and determining if there is a statistically significant predictive relationship. So in this particular case right here, we do see a negative predictive relationship, which directionally is consistent with our alternative hypothesis. However, when we look at the p-value, we see for a two-tailed test, it wouldn't be significant anyway. If we divide this in half, then our actual p-value for a one-tailed test would be 0.059. So I'll just write that in here. So it's 0.059 for the actual p-value for a one-tailed test. So there's in this case right here, we still would not be able to reject the null hypothesis because it's not less than or equal to the alpha level that we had set. So in other words, really in terms of the sampling distribution, that regression coefficient is landing pretty darn close to our region of rejection, but not quite there. So in other words, we would fail to reject the null concerning the predictive relationship between anxiety and achievement. The last variable, gender, once again, you can see that basically females were scoring higher than males on achievement, and looking at the significance level was 0.279 for a two-tailed test. Really, let's just say, for instance, I just adopted a non-directional hypothesis, just that gender would be related to achievement. In this case, the 0.279 is obviously not less than or equal to the alpha level at 0.05, so we would maintain the null concerning that predictor. So really, the only predictor that seems to be working in terms of allowing us to infer a significant predictive relationship in the population is subject matter interest. And so, when we are talking about what's really driving the association between the set of predictors and achievement, it looks like it's largely subject matter interest. Now, another little piece here is, in terms of the output, is the beta coefficients, which are basically, these are regression coefficients that are computed assuming that after converting our predictor variables and our criterion variable into z-scores, z-scored variables. So really, if we use the formula, if we converted all our variables to z-scored variables and then applied the formula for the unstandardized regression coefficient, that would actually produce the beta coefficient values that you see right here. And the reason why the beta coefficient values are useful is because they allow for sort of a relative ordering of importance of the predictors when it comes to trying to explain why the predictors are related to the criterion variable. So, again, we see that there's a significant relationship. It looks like the predictors are accounting for a substantial amount of variation in the criterion variable. So we might want to see which ones are really driving that association the most. So as we look, basically, in interpreting the beta coefficients, we would say, well, for every, let's look at subject matter interest. We would say for every one z-score unit increase on subject matter interest, there is a predicted increase of roughly 0.368 z-score units on achievement. For every one z-score unit increase on mastery goals, there's a predicted increase of roughly 0.18 z-score units on achievement. For anxiety, for every one z-score unit increase on anxiety, there's a predicted decrease of about 0.21 z-score units on achievement, and so forth. So the useful thing about the beta coefficients, though, is that they're useful for assessing the relative contributions of the predictors to the overall model. So if you take the absolute value of each of these variables, then the highest absolute value coefficient would indicate that you have the strongest predictor. So in this case, you know, 0.36, roughly 0.368 right here. Subject matter interest relative to the others is really doing most of the work in terms of explaining why there's a relationship between the set of predictors and the criterion variable. So this is really given sort of top priority, or the largest weight. You can see that anxiety has the next largest absolute value on this index, and so anxiety is really the second largest predictor. You got mastery goals that has the next largest absolute value, so that's really doing a little bit less work than the others. And then you got gender, which has the weakest predictive relationship. But again, you know, pretty much because subject matter interest was the only significant predictor, really that's the variable that's really kind of explaining most of why our predictor variables as a set are related to the criterion variable.